Very nice to be here. So I'm also directing the Quantum Technology Hub in Sensors and Metrology, which sits similar to like Miles, who's doing the Imaging Hub, on like getting information from the environment, and then there's communication to transmit that information and computation to like make sense of it, to like get something which actually is useful for all of us. And while everyone agrees like why computers and communications is useful, often we're not quite aware what sensors are doing and like why we need them. So I just want to take a step back and think about like, do we need sensors? And okay, maybe where does the word come from? Like from our senses. So if we are usually not aware of them, but if we lost one of our senses, like eyesight or hearing or touch, we would quite dearly miss that because it stops us interacting with the environment in ways we are used to. So they're actually quite essential. And just want to highlight that over the time, whenever we had like some fundamental science, a disruptive new capability to sense the previously unsensible, that made quite a big impact on like what we can do, what our lives are like. So in 1901, there was a Nobel Prize on X-rays. Nowadays, like, medical diagnosis without those was nearly impossible. Similarly, Sir Peter Mansfield in Nottingham won a Nobel Prize on the MRI, magnetic resonance imaging, which again is now in 25,000 hospitals. There are Nobel Prize on giant magnetoresistance a bit later. Why do we use that? That was high-density hard drives. Without those, we wouldn't have been able to store the information as densely as we did. And maybe most prominently, there was a recent Nobel Prize on the CCD sensor, which was effectively done by an astrophysicist wanting to see the stars a bit better. And of course, that created the whole you wouldn't be able to do selfies without that. So they can have a really profound change in what we do if we change what we can see or how easily we can see it. And so what quantum brings to it is several new pathways to make other things sensible, like gravity to look into the ground, seeing what's actually under our feet. Some people say 1 meter under London is less known than Antarctica. Because, yes, there's all this infrastructure people have put down at some point, but then forgotten about, or the buildings, everything has changed. Is anything leaking there? Are there any dangers, mine shafts, sinkholes developing? That is a major task, to look into that, and essentially what we can do to see it might have a profound impact on how we work with the future. If we can see the underground, we can start using it and have a sustainable management of not just how we live on the Earth, but also how we use the underworld. So quite important. Then we have sensors, and you'll see a gravity gradiometer outside in exhibition. I invite you to join like that and have a look. We also have an exhibit from the University of Nottingham on the brain box, because sensors can also look inside and see what parts of the brain are currently active. So when you're juggling a ball, or when you're learning to play an instrument, and all that can have profound impacts on medical diagnosis. And we all know about, actually in this room, we might be 300 people, so 70, 80 of us, when we are getting more than 80, which most of us have now an expectancy to have, about 70 to 80 in this room will have dementia. So we really want to do something about this and learn about what the brain does, how it reacts. Similarly, further sensors, extending the sensors is very, very precise timing, which can be used to actually look at the skies and see airspace much, much more precisely than could before. And all these together, this is what we're driving forward in the hub, and I'm happy to take questions later, but I see my time is up and I should hand over to, back to Katja.
Sure, thank you, Kai. Then we have Miles Padgett, Professor of Optics in the School of Physics and Astronomy at the University of Glasgow, and also Principal Investigator and Technical Coordinator at QuantIC. So this hub is developing quantum imaging for new types of ultra-sensitive cameras for medical imaging, security, and environmental monitoring, correct?
Sounds good to me. So thanks very much, and what a privilege it is to be sitting here in this incredibly famous lecture theatre, and I've had a great time looking at all the pictures of famous scientists from the past hanging up around the walls. And I think the best bit is there's one where Dewar, as a thermos flask, is presenting about how thermos flask works, and Lord Kelvin is in the audience, and it says in the caption, resting his eyes. So feel free. Clearly, if resting your eyes is good enough for Lord Kelvin, it's good enough for everybody else. So my phone, which Kai has already referred to as the timer, the egg timer, also has a fantastic camera in it. I mean, can you believe the quality of imaging that you get from your cell phone these days? But let's think about what a cell phone can't do. So Kai was already speaking about services, what goes on underneath the road. And most of the time, the road gets dug up. It's probably because someone could smell gas. And they ring up and go, I can smell gas. And out comes an entire team of people with spades and shovels, and they start digging up everything. So one of the things we've got outside there is a camera. But unlike this camera, it's a camera that when you look around, you can see gas with that camera and work out where the leak is coming from. So Kyle is there, over there somewhere, demonstrating that kind of camera. Now, another kind of imaging, says he, is the good old endoscope. And I don't know how many people have been on the receiving end of an endoscope. I won't ask for a show of hands. But most endoscopes are about the size of my finger. And you go, oh my goodness, that's not very nice. Why do they have to be that big? And it's because every single pixel in the image needs its own optical fiber. That's about 1,600 at the bare minimum, and that gives them their size. So Graham out the back there has got an endoscope which is no wider than the width of a human hair. So something the size of a human hair, you can look down it and you can have a look around in 3D, no less, as to what is out the other side. No patients involved, don't worry. Just a demonstration out there for you to see. Another thing which I think is really super cool, I was looking at it yesterday. We were outside of Westminster yesterday demonstrating our wares to some politicians, but apparently they were all busy with something. I don't quite know what. But lots of civil servants came, so that was okay. And so there's our colleagues from Heriot Watt have got a fish tank out there full of water that you can't see through. Maybe you're a diver at the bottom of the North Sea trying to fix something like pipes or whatever. And so they've got a super fancy camera that can look through cloudy water. Maybe it can also look through London fog or whatever else as a driver assistance. And so those are just three of the new kinds of imaging that quantum technology allows, and I invite you all to go out and look there. And when you're looking at it also, have a chat to the people that are there, because actually our hubs are as much about the people and the careers that our hubs enable, the people that we train for the industries of tomorrow, as they are about the research itself. And I always think that people's career paths is very interesting to just sort of explore there. Anyway, so thank you very much.
Great, thank you, Miles. Then we've got Tim Spiller, the founding director of the York Centre for Quantum Technologies and director of the UK Quantum Communications Hub. Tim, over to you.
Thank you. Good afternoon, everyone. So the hub that I run, which is, again, a big collaborative thing, so we have university partners and industry partners all across the UK. Our focus is on new, secure forms of communication. Now, we'll talk a bit more about it, I think, under questions, but one thing to appreciate is that the current ways of doing secure electronic communications that we use at the minute are under threat. So we are going to need new methods of secure communication, and that's what our work is all about. And we're going to talk a bit, I think, also about quantum physics, but I'm going to let one thing out of the bag just now and tell you that one of the fundamental features of quantum physics, and the one that's really important for our communications, is that when you try and measure something quantum, you disturb it. And that's built into nature. That's not just that the experimentalists are still a bit rubbish and they will get better in the future. That disturbance is built into nature, so we can use it. And the way we do secure communications is we take tiny quantum signals of light and send them from one place to another. And the fact that there is this fundamental disturbance means if anyone has a cheeky look on the way and intercepts your signal, they cannot avoid introducing some noise and disturbance. So you can see whether anyone is doing that. And if you can see that they haven't done that, then you can you can share secure, we call them keys, between people. And then you can use those keys for encryption or for other forms of transactions. So by sending quantum light signals around, we can effect a new method of secure communications. So in our hub, in the last 5 years, we've been pushing forward various directions of this. So one example is that in quantum communications, the transmitter's always called Alice and the receiver's always called Bob. So what we're trying to do is we're trying to put Alice in your phone for the future. So you as an individual might be able to communicate securely with your bank or the government or whatever. So we've got a demonstration on that outside where we've got a phone-sized Alice transmitter of the future. We're also trying to put both Alice and Bob on chips so they can go in computers, and we've, in the last 5 years, demonstrated the world's first chip-to-chip quantum key distribution system. So that's another demonstration. One big thing that we've done over the last 5 years is we built the UK's first secure communications network based on optical fibers. So we've got a network that's mainly down south at the minute. It runs from British Telecom in Ipswich to Cambridge. We've got a network around Cambridge. We've got a link to London. And then we're going out from London to Bristol. We've got a network around Bristol. So we've built and established that, and we are now running secure communications links over that. So that's highlights of what we've done in the last 5 years. In the next 5 years, we're going to improve on that and develop those technologies further, but we're also going to try and do satellite-to-ground secure quantum communications by sending light signals from a satellite to a telescope ground station on the surface of the Earth. So that's for the future. As I say, the UK quantum network is already there, up and running. Thank you.
Thank you, Tim. And finally, we have Dominic O'Brien, co-director of NQIT in Oxford. His expertise is in photonic systems integration, and his hub is building prototype quantum computers. So, Dominic.
Thanks. My memory of this place is, of course, as a kid, watching the Christmas lectures on telly. So it's very strange to be the other side of watching of that barrier. So in this phone, if I bought an expensive iPhone, there'd be about 3 billion transistors. Now, I looked up this morning, and the first microprocessor had about 2,000 transistors in it. And that's taken 50 years, 1970 to 2020, something like that. So we've seen this immense growth in the power of computers that we all have in our hands, around the place and things. But there are still problems that we find it hard to solve. Things like even how the order you might deliver parcels, that sort of thing. You have a delivery route. How do you find the most efficient route? That's quite a hard problem. It grows much harder as the number of parcels you need to deliver goes up. So those sorts of complex problems, which are parts of our lives, how do we run complex cities, those sorts of things, where actually having more powerful computers or computers that do computation in a different way will be useful. Quantum computers can do that. Now, I'm sure we'll get into the quantum physics a bit later, but quantum physics are built with, rather than the digital bits, the ones and zeros that we see every day, they're built with quantum bits. And the odd quantum thing about a quantum bit is it can be both a 1 or a 0 at the same time. And it can be a bit of 1 and another bit of a 0 at the same time. So and that allows you, if you build a quantum computer, to have, rather than, if you have a normal computer, there's a pattern of 1s and 0s, and that will be a particular piece of information. In the same space, you can store many possibilities, if you like, many patterns of 1s and 0s in that same space. And it's that storage, if you like, of simultaneous possibility that gives you this way to do some very hard problems that you wouldn't be able to do with normal computers. And in the hub that I'm a part of, I'm privileged to work with some much smarter people than me, trying to build the elements of quantum computers. Now, in a quantum computer, what are those elements? How do we create those patterns, if you like? You can use ions, so they're atoms with some electrons knocked off that sit in a vacuum. And you can apply electric fields and magnetic fields and optical fields to turn around the patterns, the states of those things, and manipulate, if you like, the quantum bits. You can use superconductors and we do work in that particular technology. You'll have seen results from Google and IBM. They're artificial atoms, if you will, made from superconductors. The hard thing is that the world is quantum, but you never see this stuff unless you cool it down or just remove all the sources of noise. So the key challenge for quantum computation that we're looking at now is doing are those sorts of things. And it's a lot of hard engineering. There's a lot of smart people working on this globally and in the UK. So once we have these machines, we might be using them for things like designing new materials, more efficient wing design, more complex planning of the way we live our lives and the way that cities work, the way the health service works, those sorts of things. There are all these sorts of applications that may be possible in the future. I'd like to finish by saying, echoing what Miles said, that there's a demonstration, a virtual demonstration of one sort of computer outside. Go and have a look at that. But also, this is an exciting area. If you're at all interested in a career in science or in engineering, we're way short of engineers in the UK, way short of scientists. This is a really great area to get into.
Great.
Thanks.
Thank you, Dominic. So before we actually kick off the actual discussion, I'd like to ask you guys a fun question. So when we talk about quantum, I guess you all know that we are talking about very, very, very small things, right? Teeny tiny, so it's the scale of atoms, subatomic particles, electrons, protons, neutrons, quarks, gluons. But my question is, what's inside actually? What is that? Do you think they are particles, or maybe they could be waves? Now, by a show of hands, who thinks that they are particles? Anyone? Okay, a few people there, yes. Who thinks they could be waves? Okay. Well, what about both particles and waves? Yay! Fantastic, great. Exactly. So, and I personally find it mind-boggling how it could be both particles and waves. But yes, it's called wave-particle duality, and it's not the only cool property of the quantum world. As Dominic was just saying, when a qubit can be in multiple states at the same time, that's called superposition. And it's also really cool. For example, if you flip a coin, right, and the coin is turning in the air, and while it's in the air, you don't know whether it's heads or tails. So basically, it's in the superposition of states, superposition of heads and tails at the same time. Or maybe you've heard of Schrödinger's cat, right? The cat in the box, and there's a mechanism, and until you actually look into the box, you don't know whether the cat is dead or alive, right? And so basically, the cat is dead and alive at the same time. Actually, for my toddler, whom you heard earlier, I bought him a book, a baby book, Quantum Physics for Babies. And, and the author actually changed that experiment slightly, and the cat is now either awake or asleep, which for me, I found, I always found it a bit of a problem that the cat is either dead or not. So, and the other really cool property of quantum mechanics is entanglement. And so imagine a particle here and the other particle really far away, light years away at the other end of the universe. What's really cool is that when this particle here changes state, the other particle will automatically be in the same state as well, which I find amazing. So there's like this mysterious connection, kind of similar, when maybe, I don't know, if you fall in love and your partner goes really, really far away, and then if he's sad and you're sad, and he's happy and you're happy, but I guess he would have to communicate it to you somehow first, like, I don't know, send you a WhatsApp message or something. But for particles, they can't send a WhatsApp message, so they just know automatically, and they can be in the same state at the same time, which is really, really crazy. So that's quantum mechanics, but now let's go back to our panel. And the first question I have actually for you, Kai, can you tell us what devices are we already using in our daily lives that are actually already based on the principles of quantum mechanics?
Yes, so essentially quantum technology itself is not new, or at least we're all using effects of quantum mechanics. It came actually, what is quantum? You heard about all these spooky effects, but what is it in the basics? And it came about in 1899 when Max Planck was posed the problem of actually how do we understand a spectrum of light emitted from something heated up. The lamp industry was at that time quite interested to know how do we make the light bulbs a bit more efficient. But people in physics, that was a big puzzle because that spectrum from something black, which we heat up and then it starts to send out light, it was not explained by the theories, or it was inconsistent with the existing theories. And what Max Planck did, he ad hoc introduced just an idea to say, actually, what if the light didn't come as a continuous form of energy, but in little packets of energy? So if it was something which is not just a wave, but it comes as little photons, which each has a certain amount of energy. And with that idea, he was able to explain the spectrum. He was very unhappy about this because he said, yeah, this is just an ad hoc idea and I have no reason why it should be like this from the physics, but it seems to work. And that essentially started quantum mechanics because this idea that we have essentially little packets of energy, like quanta, it doesn't come continuous, but in quanta, that essentially is behind it. That then moved on, and in the 20s, that was golden age of the Gedanken experiments, thinking about, what does that actually what are the implications? People came to realize that actually it's not just photons which act as a wave and a particle at the same time, but also electrons and atoms and effectively all particles. And what does that imply? If we have to treat them as waves, that then explains the energy levels of electrons around atoms, that we have actually energy levels. When you look at the orange street lamps, or the old ones, the sodium street lamps, that is actually a transition between two energy levels in sodium atoms. You'll see the same orange light. If your parents are around, you might do this experiment at home. Put some table salt inside the gas burner or a blue light flame, and you'll see this orange light coming from the table salt because that's the sodium line, and that's the same which is used, sodium is also used in these street lamps. So that's the quantum effect that we have these. And of course, it led us to understand this wave nature. It led to understand, okay, electrons in solids move like waves, there are energy levels. So all the bands in semiconductors, so how does electron transport in materials work? And so effectively, any transistor is effectively based on our understanding of quantum theory, which means every computer, every piece of IT equipment. Similarly, lasers, that we learned how to actually create these bits of photons, these quanta of light in a very coherent way, like running all our communication networks or our DVD players or Blu-ray players. All that is quantum technology. So we all carry what we call nowadays quantum 1.0 around in our pockets. So what's the special thing about why is everyone excited and putting lots of money into quantum technology right now? And that is because we are now at the we have reached the technological ability to manipulate the single particle nature, to get to actually the quantum effects at a single particle level, not just the averaged effects of these waves. We can see the single wave or the single particle be in a superposition of two states at once, or actually entanglement between two particles in two different places, that they know somewhat what the state of the other is. And so that was a technology advance which we can now start to harness, and that opens up lots of new technological capabilities. But you actually also carry something of that around, not quite in here, but you're using it with your smartphones. When you ever look on a map and try to find your way, when you navigate, because that interacts with the global satellite navigation network, and each of these satellites has an atomic clock on board, which effectively is the quantum technology of this quantum 2.0 type, probably the oldest one. Invented, the first atomic clock was working in NPL 1957. The UK was maybe not best in harnessing all the power of this, that gone largely to other nations, but that's why we have this program to make sure with the hubs to translate into industry, keep it in the UK. But these atomic clocks, they put electrons in a superposition of two different energy levels around the atoms, and with that can measure time very, very precisely. And we need this precise time measurement on the satellites to measure the transit time of a signal from the satellite to our phone. And if you know how long it took for the microwave signal coming from there to reach our phone, we know the distance. If we know the distance to 3 satellites, we can start pinpoint our position. So we're all using Quantum 2.0 technology already, and it's just that there's much, much more to be gained, and that's where we're heading.
Great. Thank you. So with all the research and all the money being spent on quantum, on taking quantum out of the lab, how do you think, maybe Miles, question for you, how do you think the UK will actually benefit from all this commercialization of quantum mechanics?
So, I mean, let's have a think about what universities do. Universities train people, and probably the biggest impact that universities have are the careers that we enable with those people that then leave and work for UK-based companies. And so we're reflecting on, certainly within our own hub, and I'm sure it's true of the other hubs as well. You know, we started off 5 years ago. Many of the people that we employed, either as students or as what's called postdoctoral researchers, so that's people that's just got their PhDs, have effectively now moved on in their careers from our own hubs and now work for UK-based companies. And ultimately, the transfer of technology, I believe very strongly, is often a people transfer. It's about the outflow of people.
Yeah.
And so I just want to say that right at the start. Now, the other thing, of course, that we try to do is inspire new products for companies to make. And one of the really exciting things I think about this program as a whole is, as well as funding research, and when people talk about funding research in universities, what they really mean is funding people. And most of the money that is spent is actually funding people. We also set aside 20% of our recurrent budget to trigger new projects. And many of those projects have been joint projects between UK-based industry and the universities, with a view of initiating new products for those companies. And I think all of the hubs can give specific examples of things that you can now buy, not necessarily in Sainsbury's, okay, it's not that kind of shop, but in a scientific product sense of things that one can buy as a result of the work that has taken place in our hubs. And that ultimately will be the success by which our hubs are measured. It is, can we make sure that the UK does not get left behind in the next quantum revolution? Can we support high technology companies with, one of the companies we work very closely with us, in fact, you work closely with them, we all, I think, work closely with them, is at M Squared Lasers. It's a company in Glasgow. They employ about 100 people, many of whom used to work in one or more of our research groups. And something like 85% of all their products go to export. And those are the kind of companies that the UK economy is going to have to grow if we are going to carry on generating the tax revenue to fund our NHS and all of the other things that we want a government to support. And I think all of the hubs take that responsibility extremely seriously, as indeed we should.
Great, thank you. Yeah,
Could
Tim?
I just add to that?
Absolutely.
Yeah. So I absolutely echo that, and I think if we look over the last 5 years, from when the UK program started to now, there is a number of big UK companies already established who have now got significant interest and who are investing themselves in a quantum aspect of their R&D now. Yeah. But in addition to that, over the last 5 years, a considerable number of startups have emerged in the UK, which is very refreshing to see. So there are these two ways forward with industry. There are startups that have very often come out of a little university group with some new idea, but there's also big companies that are picking up on this now. And I think those two going forward together in the UK means we've got a very good and now well-established industry that's growing.
Yeah, absolutely. Yeah.
Well, I was going to say, I think you reach a point where there are enough startups, there's a vibrant community that our younger researchers are willing to take the risk with a startup, and that wouldn't have been a traditional career choice for them.
Yeah.
So it's actually been a rather virtuous circle. They see some success. They see that even if this particular venture doesn't lead or something goes wrong with it, that's fine. They'll find something else to do, and there's enough confidence in it. So it's actually been a good story because of the sort of critical mass that actually, the investment that was made half a decade ago.
Great. Actually, Dominic, I have a question for you now as well. I'm sure people here are all interested in quantum computing because it's been all over the news recently with Google. How different are quantum computers? Are we going to have them at home? Are they going to replace our laptops, or is it going to be something completely? Can you describe one? Maybe I'm not sure whether people have seen one.
Well, I think there's several things to say that what we understand about a silicon chip is that we all have some vision of something that sits in a little package that's glued to a circuit board on our phone. And within limits, most silicon chips are the same. They use roughly the same technology. They're roughly made in the same way. In quantum computing, there's not one clear way to do it. So there are different approaches. So you'll see something about ions outside, superconductors. Now, other things too. Each of them has their own real challenges. To get the quantum effects, it needs to be very quiet, very low noise. So they're either in big refrigerators because they need to be cooled down just above absolute zero, that's superconductors. And one of these fridges would maybe 5 or 6 meters high, a meter wide, nothing like the computer you'll have seen. They're very, very different with wires and things coming out. I call it steampunk computing on some days because actually it's very much like you would draw a computer if you didn't quite know there was a silicon chip. And an ion trap computer, the ions have to be held in a vacuum. There's lots of laser beams running in, all of those sorts of things. And because it's early days, that sort of integration that's taken something really big and made it really small, So think of it like an old CRT TV, a 65-inch CRT TV, if you can remember one, used to be about 65 inches deep. 4 people would have to lift it. And now technology changes and it's a flat panel. So because a quantum computer, we haven't seen that integration and development. They're big structures, they have to be cooled, they have to be in temperature-controlled environments. So not like a laptop. What I would say, though, of course, is we don't see what a Google server farm looks like. So communications means we access vast machines the size of warehouses with cooling, all of the same sorts of things that a quantum computer has. So the fact it isn't a laptop doesn't necessarily make it any less useful. It's just much harder to do. And there won't be so many to begin with. I'm not going to make the IBM statement.
As you probably know, there are a number of companies working on quantum computers right now. IBM is one of them. There's Google, and there are some startups as well. But are they actually already better than traditional computers, or still not? Where are we with quantum computing?
Where are we? It's great because when the Google announcement came out, we saw, did people see? Did we put hands up? We saw the Google announcement. Yeah. There was a sort of internal debate about what it meant. Now, I'm an engineer. I just thought fantastic engineering, absolutely fantastic engineering efforts. I think it was about 70 people working for 5 years. Really superb. A necessary milestone on the way. You need to. It's hard stuff, it truly is. Now, what they did was they showed they could do a problem, and it was a test problem, which didn't have practical use, which would have taken a conventional machine, a big Summit, which is the world's biggest supercomputer, 20 megawatts of power, huge thing, a long time to do. Now, whether that's supremacy or not, it seems to me that's not quite the point. The point is we're at this cusp. We're starting to see real practical technology where you're seeing it does things it's hard for something conventional to do. We're sort of in this crossover region. What I should say is the view is that to do practically useful problems, because this was a test problem, is still some way off. But necessary step, fantastic engineering. You know, you can see we're in a region that we weren't in 5 years ago, I think.
Yeah, great. Tim, question for you. What are the dangers of quantum computing in your view?
Okay, so I'm the communications guy, and one of the problems. So it's very interesting in the quantum technology arena, because quite often things are worked out theoretically about what you could do with quantum technology when you have it in the future. And one of the things that was worked out actually quite a long time ago now, 1995, Peter Shaw worked out that if you had a big quantum computer, so this was thinking very theoretically at that point, one thing you could do is break the mathematical algorithms that we currently use for our secure communications. So at the minute, the way we do a lot of our secure communications, or at least the way we start off secure communications sessions, is that we use what's called public key cryptography. And this is based on the fact that there is a mathematical problem that is easy to do one way and hard to do the other. And it's taking two very big prime numbers and multiplying them together. If you do that on a big computer, that is very easy to do. On the other hand, if you just give someone the product of those two primes and say, find what the two primes are, given their product, that is incredibly hard, and nobody knows how to do that efficiently with an ordinary computer. So at the minute, current cryptography is based on this asymmetry in this mathematical problem, the factoring of a composite number into two primes. And Peter Shaw worked out in 1995 that if we could build a big quantum computer, you can solve that problem easily. So if there was a big quantum computer around right now, all of the secure communications that we're currently using would effectively be very vulnerable to this. And so we have to think ahead. And actually, there's an aside on this. If you're communicating stuff currently now that has a very long security shelf life, so it's data that you want to be secure for 20 or 30 or 40 years, maybe you should be worried now, because people can record that encrypted data right now, and they can potentially decrypt it in the future. So if you're worried about very long security shelf lives, you should be worried about secure communications right now. If the stuff that you wish to communicate has a very short security shelf life, so you don't mind if somebody finds it out in a few days, then you probably don't need to worry yet. But when a big quantum computer comes along in the future, we're going to need new secure communication methods, which is why people are already working on these, because we will, over time, need to implement them in the future.
Thank you. Okay, let's step away from quantum computers for a second and talk about sensors. So, Kai, question for you. Can you describe some of the new disruptive sensor capabilities that quantum sensors will have? How are they going to be different from what we already have today?
Yeah, I already mentioned that a bit earlier, and Miles mentioned about looking under the ground and trying to see the infrastructure which is there. So why would this be important? And okay, I as a physicist was it needed a bit convincing that to get enthusiasm of like looking under the ground and seeing the infrastructure, but actually it's a big problem. And we all are annoyed by when people dig up the roads and you are stuck in a traffic jam. So if you could actually replace or put the new next high-speed broadband in with horizontal drilling, which in principle the technology is there, but people are afraid to hit a gas pipe or electrical lines. If we could see that more directly or knew exactly where it was, we could avoid a lot of these disruptions. Similarly, when we want to go like HS2, if you're thinking through an old mining area, Birmingham, Manchester, that area, lots of mine shafts. At the moment, you have to just drill and look, can you find them? If you could find them with a sensor, that would be much less disruptive and would use much less money to actually do that. And it's like a study in the Netherlands, some numbers from there suggest that it's about 0.5% of GDP going into delays and cost overruns due to us not knowing what's under the ground in infrastructure projects. Of course, there's also oil, minerals, carbon sequestration. If we want to take the carbon out of the atmosphere, put it down, we have to make sure it stays there for 6,000 years or so, which is the carbon cycle time. But one issue is you put it down and you can see it at the start because it has a nice boundary between the gas or the carbon dioxide phase and the groundwater which might be surrounding it. But eventually it gets dissolved. You get something like fizzy groundwater, and so you can't see it with traditional technologies very well. And gravity, again, the mass of the carbon is still visible, so that one can refine the models and know exactly what's happening and monitor how the plumes might evolve under the ground, so that you're sure it does it in the right way. And you can even look deeper into magma flows, and eventually one might hope to be able to tell when a natural disaster like an earthquake or volcanic eruption might happen. So all these things are opened up by these new sensing capability. The other thing, I spoke about the brain, and you should really go to the stand outside, seeing what part of the brain functions. But I also want to mention the airspace control. Actually, we are just approaching a new revolution. At the moment, UK airspace looks at about 7,000 flight movements every day. Once we have flying taxis and drones, it's likely to be 1 million or more. So we'll have lots of movements in the air. In Australia, Amazon is already delivering parcels via drone. I don't know if they already have any anti-collision mechanisms so that when two drones try to deliver, they don't hit each other. I guess that's a sufficiently less low-density populated country that it doesn't happen. What happens if you have lots of them in flying taxis in front of an environment, like in a city environment, lots of trees and houses which scatter and lots of obstacles? You have to have a completely new approach to airspace control. And that might mean much better radar systems with higher resolution and picking out things out of the scattering, or some of Miles' sensors to pick up, look around the corner if something is approaching around there, not just on the ground but in the air. So all these things will be needed to move forward in our way how we transport things and how we get our deliveries.
Yeah, fascinating. And let's talk about medical technology as well. Miles, a question for you. How will quantum transform medical imaging and other medical technology?
Well, as I've already mentioned, the endoscope type
Yes, you did.
system. Let's not relive that experience. So we've got a number of other things. I can't remember who spoke about. One of you spoke about X-rays before, and X-rays I think are the ubiquitous through body imaging technique, both for medical and indeed airport, whatever. But of course, X-rays aren't particularly good for you, and I think we all have some nervousness about that, and indeed that's why the person that runs the X-ray machine doesn't stay in the same room as you have your X-ray in, because they're trying to shield them from the X-rays. And so we'd like to use X-rays for lots of things that we don't. We don't like X-raying the brain at all, for example. We consider that not a great thing to do. So you go, well, how about I use light instead? I'll use light to look through the body, and you sort of can do that a little bit if you, on a night time, if you go outside and get a bright torch and you hold it to your hand, you sort of see some light comes through. So light does come through the hand, but on the other hand, I don't really get to see the bones. And then one of the things that we're able to do now with quantum technologies and the kind of camera that Gerald and his colleagues have from Heriot-Watt today, looking through the water, is that you can shine the light, and actually, some of the light goes straight through, and that would be okay, but the other light bounces around a lot inside the hand, and that's all fuzzy. So what I really need is a camera that only looks at the first light and ignores everything else. And then, sometimes it's called prompt imaging. I'm just going to look at the first light, and then I can see through. And then you couple that with what are just now amazing computer algorithms. We've got some of those on display as well, which can somehow make sense of this fuzz. And that's actually the key to how we see through the fiber. You look through the fiber and it's a mess, but it's always the same mess. And so the computer can sort of learn about that and then do the inverse and recover the image. And so this combination of being able to detect the single particles of light. In fact, the first experimental evidence for that, we're talking about Nobel Prizes, 1905. You may have thought Albert Einstein won the Nobel Prize for relativity. Nope. You may have thought he won it for something else. Well, he did. He won it for what's called the photoelectric effect, which was essentially pretty much the first experimental proof that light was particulate, it came in particles. And we were talking about wave-particle duality. I was very excited to see there's a portrait of Thomas Young hidden behind the Quantum City stand. He was the first person to show that actually light was a wave, and so there's been experimental evidence for both. But once you recognize that actually light is particles, and you can make cameras that are so sensitive that you can see these individual particles, and you can time to a few picoseconds, and then a picosecond light's traveled a fraction of a millimeter. You think of light's very quick, but it's only gone a fraction of a millimeter. That timing, that sensitivity, that computing power means that you can recover images in situations where if you and I looked at it by eye, it's just a fuzzy mess. And that, I think, is a really exciting. Imagine the prospect of being able to do an MRI with a torch. So that's the kind of thing that quantum technology offers, or indeed with Kai's work, measuring the precise magnetic fields associated with
So
stuff.
when is that going to happen?
Actually, we do have some images of bones in your hand. So let's see.